My name is Ashwin Pathak and today I'll be covering up the following topics: Hermite polynomial, Laguerre polynomial, moment of inertia matrix and rocket dynamics using Hamiltonian Lagrangian mechanics. So let's see our first topic, that is Hermite polynomial. So Hermite polynomial can be standardized into two forms. First is probabilistic Hermite polynomial, which is h e n of x equals to -1 to the power n e x square by 2, the nth derivative of e to the power minus x square by 2, and physicist Hermite polynomial, which is h n of x equals to -1 to the power n e to the power x square, nth derivative of e to the power minus x square. So let's see the graph. For the probabilistic Hermite polynomial, we have the following graph. Here this broad line is for n equals to 0. This circular line, circularly dotted line is for n equals to 1, and this dotted line is for n equals to 2. Now for physicist Hermite polynomial, the graph is shown over here. So you can see the differences just of the constants, and it can be standardized using some manipulations. We define the Hermite polynomials from a generating function. We define Hermite polynomials by a generating function g x of t as e to the power minus t plus 2tx equals to summation of n equals to 0 to infinity h of n x t to the power n by n factorial. Now we differentiate it with respect to t. So we have minus 2t plus 2x e to the power minus t square plus 2tx equals to sigma n equals to 0 to infinity h n x and t to the power n minus 1 by n factorial. Now we expand the term and put the generating function in this again. So we get minus 2 sigma of n equals to 0 to infinity h n x t to the power n plus 1 by n factorial plus 2x sigma n equals to 0 to infinity h n x t to the power n by n factorial equals to sigma n equals to 1 to infinity h n x t to the power n minus 1 by n minus 1 factorial. Now we relabel minus 2 sigma n equals to 1 to infinity and h n minus 1 x t to the power n by n factorial plus 2x sigma n equals to 0 to infinity h of n x t to the power n by n factorial equals to sigma of n equals to 0 to infinity h n plus 1 x t to the power n by n factorial. Now we equate the coefficients of t to the power n. So we get h n plus x n plus 1x equals to 2x h n x minus 2n h n minus 1 x t to the power n by n factorial. Now we differentiate g of xt with respect to x. So we get equals to 2t e to the power minus t square plus 2tx equals to sigma of n equals to 0 to infinity h of n x h dash of n x e to the power n by n factorial. Now we stick this in g. So we get 2 into sigma 2 to n equals to 0 to infinity h of n x t to the power n plus 1 by n factorial equals to sigma n equals to 1 to infinity h dash n x t to the power n by n factorial. Now we relabel and we get 2 into n equals to 1 to infinity h of n minus 1 x t to the power n by n minus 1 factorial equals to sigma n equals to 1 to infinity h dash n x t to the power n by n factorial. Now again we equate the coefficients of t to the power n and we get h dash n x equals to 2n h n minus 1 x. Hence Now we can use these recurrence relations to derive the Hermite differential equation as from 1, 1 and 2. We get h of n plus 1x equals to 2x h n x minus h dash n x. Now we again differentiate it with respect to x, and finally we get h and double differentiation of h and x minus 2x h n dash x plus 2n h n x equals to 0. This is known as Hermite equation. On Laguerre polynomial. Laguerre polynomials are the solutions of Laguerre's equation, which is x y double dash plus 1 minus x y dash plus n y equals to 0. Now these polynomials are the polynomial sequence which can be derived from this formula. Ln x equals to e to the power x by n factorial, nth derivative of e to the power minus x into x to the power n, which is also equal to 1 by n factorial d by dx minus 1, the whole nth derivative into x to the power n. We'll have a look on some of the polynomials like L0 x equals to 1, L1 x equals to minus x plus 1, and L2 x equals to this parabola. These polynomials can be geometrically represented in this graph. Now we'll see about generalized Laguerre's polynomial, which are the solutions of the Laguerre's equation x y double dash plus alpha plus 1 minus x into y dash plus ny equals to 0, where alpha can be a constant. Now we have also seen that there's a relationship between Hermite polynomials, which is covered in the last part, and this part, Laguerre polynomial, which is h2n x equals to minus 1 to the power n, 2 to the power 2n into n factorial, ln minus 1 by square root of ln of x square, and h2n plus 1 of x equals to minus 1 to the power n, 2 to the power 2n plus 1 into n factorial into x into square root of ln of x square. So this was Laguerre polynomial. Moment of inertia matrix. So consider a rigid body rotating about an axis with angular velocity omega. Now consider the ith particle at a distance of ri from the center, from the axis. So dri by dt equals to omega, cross product of omega and ri. Now angular momentum, as we know, is the sigma. Angular momentum of the whole rigid body is the sigma of each particle into mi ri into dri by dt, which becomes equal to this as shown over here. This L angular momentum can also be represented in the matrix form as the shown here. Lx L by Lz equals to the Ij matrix and the angular momentum matrix. Here Ixx equals to sigma of I equals to 1 comma m into yi square plus zi square into mi, which is the integral of y square plus z square into dm if we consider small particles. So we get Ixx is the moment of inertia about x-axis. Similarly, Iyy is the moment of inertia about y-axis. Izz is the moment of inertia about z-axis. Ixy and Iyz, Ixy and Iyx are the xy product of inertia, and likewise yz, zy, xz, zx. So this matrix is known as moment of inertia tensor. So we get moment of inertia matrix and moment of inertia tensor are closely related, or they can also be called same. So here it is the moment of inertia matrix. Study about rocket dynamics. Consider rocket with attributes q and q dot, and the mass of the rocket at the given instant is m. So we have kinetic energy equals to half m q dot whole square. Potential energy equals to mgq. Now Lagrange's equation is given by L equals to k minus u, which we get as half m q dot square minus mgq. We also know that about the Lagrangian equation that d by dt of dou L by dou q dot equals to dou L by dou q. Dou L by dou q dot equals to mq dot, and dou L by dou q equals to minus mg. So we get d of dt of mq dot equals to minus mg. Then mq double dot mq twice differentiation of q plus dm of dt into q dot equals to minus mg. This is the Lagrangian equation. Now we see about the Hamiltonian equation. H equals to k plus u. Hence we have half m q dot square plus mgq. We know that dp by dt equals to minus dou h by dou q. But we also know that T equals to dou L by dou Q dot, which is equals to mq dot, and dou H by dou Q equals to mg. So we have d of, and we put these two in this equation over here. So we get d of mq dot by dt equals to minus mg. Hence we get mq double dot plus dm by dt into q dot equals to minus mg. This is the Hamiltonian equation. Hence we can check that Hamiltonian and Lagrange's equations come same.